All right, welcome back. So, how do we know that climate change is a legit thing? Um, and how do we know that taking one example of weather and using that to define a location's climate is bad? Well, we need to actually unpack the scientific method and able to do that. So let's talk about the scientific method. First off, what is science? Rather than that scary class that you were afraid to take or that you don't think you're good at, I always hear that you're bad at science. Believe it or not, you're actually a great scientist and you don't even know it. And I'll explain why in a few minutes. Um, but what actually is science? If I found you on the street and offered you $1 million to define science, what would you say? Well, here's what I would say. Science is the systematic study of everything around you, the world around you, through observation and experimentation. In layman's terms, science is the study of everything. So think about this. Um, Studying the best way to get to school. If you've ever done that before, either as a child, which streets were the easiest to take to school, or which bus route was the easiest, or as an adult, which freeway is the easiest, which road is the most convenient, guess what? You have done science and you've actually done it really well. Um, if you've gone to Starbucks and tried a bunch of different coffees over time before you decided, hey, I like my Trenta iced coffee with 2 pumps of mocha syrup. That's my favorite. That's science. Taking data that you have collected over time and making conclusions based off of it is science. If you are a social scientist, that is science. If you are a political scientist, that is science. Yes, I am not one of those scientists who says, no, those aren't sciences. No, those are definitely sciences. Why? Because science is the study of everything. So yeah, you are all excellent scientists. So coming into this class and saying, hey, I'm not good at science. No, 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 you are great at science. We've just made it look way harder than it's supposed to be. That's something I'm going to try to break down in this class. All right, off my soapbox now. The other part of this definition that's really important is observation and experimentation. What do these two things mean? Well, observations are simply collecting data without doing anything to the system that you're observing. So if I walked outside with a thermometer right now, held it up in the air, and measured the temperature, that is taking an observation. If I gave you all a test, didn't do anything else, just gave you all a test, didn't manipulate anything, didn't change anything, just gave you all a test, and then you all took it, I got it back, that is collecting data without actually doing anything, without making any changes. So that is an observational study. On the other hand, an experimental study is actually manipulating the situation and observing the outcome. So for example, let's instead decide that I decided to study the effects of alcohol on test scores. So I take you all, I give you a test, collect the data. Then I take you all out for a round at happy hour, get you nice and liquored up. I know many of you are under 21, so obviously I would never do that. But then got you all liquored up, put you back in the room, gave you the exact same test, and then saw how the scores changed. That would be an experimental study. What I have done is I have changed the situation. I have manipulated it. I gave you all booze, got you all liquored up, and then had you take the test again. That is an experimental study. Another good example of experimental studies, weather forecasting. As meteorologists, what we actually do is we tweak the atmosphere very slightly and we see how it responds using climate models or for weather using weather forecasting models to then make a forecast. So that is an experiment. So observing something is simply collecting data without manipulating it, without changing anything. Experimenting is taking something and tweaking it, changing something about it, introducing some variant, some variable, something new, and seeing how it affects it. Um, that being said, either observations or experimentations both follow the scientific method. Now, I'm sure many of you have heard about the scientific method at some point in your life. Um, you've probably seen it on a poster in a K-12 school. You've probably heard your friends talk about it. You may have even seen like some video about it. But what actually is it? Well, it's the sequence that scientists use to do science. Um, and there are 6 main steps. The first step, which ironically is the hardest step, is to identify a problem, to figure out what you're going to study. Um, Up to this point in your academic career, chances are you've been given the problem or you've studied a problem that already had results, somebody else had already done it. But that is the first step, identifying a problem, figuring out what you're going to research. The second thing you want to do is you want to collect as much information about the problem as you can. You want to educate yourself. So then you can propose a hypothesis. A hypothesis is an untested explanation and oftentimes referred to as an educated guess, taking what we already know and making a conclusion based off of it. That being said, that hypothesis up to that point is untested. The only backing you have for it is prior knowledge. So now what you have to do is you have to test the hypothesis. You have to take it and design an experiment to test it. You need to throw it through the ringer. Now, it's very important that your experiment tests your hypothesis. So if my hypothesis was that alcohol lowers test scores by 20%, and I gave you all a test, and then I gave you all coffee, and then gave you another test, would I be testing my hypothesis? No. I'm testing the effects of coffee in this case. But my hypothesis was regarding the effects of alcohol. So my experiment in that case does not test my hypothesis. That's bad, okay? So I want my experiment to test my hypothesis. Now, once I've figured that out, once I've made sure that it tests my hypothesis, I run the experiment. On the other end, I get data. I get results. And what I want to do is I want to collect and organize those results. Put them on the graphs, put them into tables, make them easy to read. But guess what? That's not enough. I can't just say, here's the results, have a good day. No, I need to actually interrogate these results. I need to run statistics on them. I need to take averages. I need to study trends. I need to look for correlations. I need to analyze the results. In essence, I need to throw them into an interrogation chair and have Chuck Norris do his magic on them. That is called analysis. I need to analyze the results. Once again, taking averages, looking for trends, testing for statistical significance. That way, I can then come out the other end and say, well, based on what we know to be tried and true methods of analysis, my results either support my hypothesis or don't support my hypothesis. And that is where you get to your conclusion. Your conclusion then is, okay, so these results from this experiment support my hypothesis, or these results do not support my hypothesis, or these results support a hypothesis that's already been tested, or these results reject a hypothesis that's already been tested. This method is very, very flexible. What that means is that very rarely is it this pretty. You identify the problem, you propose the hypothesis, you design the experiment, you collect and organize results, you analyze them, you draw a conclusion. Um, that is not real life. That is the cleaned up, pretty version that we present it in. But the reality is that things happen. Um, you may make an observation and identify a problem, and then halfway through your study realize that, hmm, this wasn't quite what I was looking at. This doesn't quite add up to what I was looking at. So now you have to change your problem. That means you have to go back to the drawing board. Uh, you may design an experiment and get results that actually bring something else totally to light. You may actually discover something by accident. Um, Believe it or not, if you've ever taken penicillin, used a microwave oven, or driven using rubber tires, all three of those things, penicillin, microwave ovens, and rubber, were discovered by accident, meaning that there was another experiment that was going on, and somehow, some way, this came out of it. That happens all the time. You may run out of funding and have to then change your experiment to either meet funding requirements or to work with the funding that you currently have. Um, you may take your results, take them to a conference, have other people look at them. That's called peer review. And they may say, well, you left this out. Or what about this situation? Um, or, yeah, that metric might not work. You might want to try this one instead. That is a refining process. And you go back and you take your experiment, you tweak it, you update it, and then you see, do the results still support your hypothesis? So it's very flexible, but it's also very complicated. Um, this is a more realistic vision of the scientific method. This is what is called the activity model of the scientific method. And rather than it being just a clean sequence of things, instead, it is these different steps that can be taken in any order. But at the end of the day, every single one of these steps wraps around questions. At the end of the day, the scientific method has questions at the center of it. And everything we do in science is seeking to answer questions. Whether you are a political science seeking to understand how a former president can incite an uprising, or you are a social science trying to understand how COVID-19 has caused depression, um, or you're an economist trying to understand why the stock market is doing so well while unemployment and jobs and Main Street aren't doing so well. Um, those are all different sciences that seek to answer questions. So no, science isn't just an old person with a lab coat on, swinging around a test tube full of chemicals. Now that is science too, but so many of those other things are science as well. Now that being said, as you carry out your experiments, there's a lot of terminology that comes up at the end. How many of you have ever heard of the phrase, that's just a theory, or, I have a theory? I have. But what is the difference between those? Well, we'll talk about that next time. We'll talk about that next time.